the big point of these trig identities for this unit is for us to simplify trigonometric expressions. And what that means is we want to get one, if we can, one term by itself. We want to get one term alone. That's like what simplifying trig expressions means. Sometimes you can't get it to just be one term by itself, but you want to try to get it to be as little terms as possible, like normal simplifying. So strategies that we'll use, we're going to substitute using these trig identities we just talked about, and we'll add more in later. So we're going to substitute using trig identities. So we'll do that to try to cancel things out, to turn two terms into one, to get rid of a fraction, because that's not simplified. We want to get it to not be a fraction if possible, etc. There's other things we will talk about. Some things I want to look out for. So things to look out for when simplifying. I know sine squared of x, if I see it with cosine squared of x or 1, these things go together. And I can probably rewrite them in some way to make it simpler. I know cotangent squared of x or theta goes with cosecant squared of x. That comes from the Pythagorean identities, and 1, these three things go together. And then I know if I see tangent and secant together, tangent squared and secant squared together, and 1, I can rewrite those as well. So secant squared of theta, or x, tangent squared of x, and 1, those three things go together as well. Things to look out for. Other strategies, I want to try to factor, because that might help me. So I might use GCF, I might use the diamond method, I might use the difference of two squares, any factoring method we've talked about before. Another thing I want to try to do is get a common denominator. I might have to do that to add fractions together to make them like turn two fractions into one. Maybe I need to get a common denominator and actually combine them. Maybe I want to multiply the denominator by a conjugate. That might help me. So multiplying the denominator by a conjugate might help me. Maybe I want to split up a fraction into two separate fractions. Maybe that will help me get rid of stuff. So the opposite of getting a common denominator. So split up a fraction into two separate fractions. And then lastly, like if all else fails and you can't figure things out doing any of those methods, to simplify, maybe you just rewrite everything in terms of sine and cosine and then just cancel stuff out. So rewrite everything in terms of sine and cosine as much as you can so that you can cancel things out. Okay, so we're going to go down to example 2 to do an example of this simplifying trig expressions. And we're going to look at A. So I have cosecant squared of x times cotangent of x minus cotangent of x. And I want to try to get this to be one term. The point of this is to write as one term if I can. I want to try to get it to be one term. And no fractions. I want no fractions. That is what simplifying is for trig identities. So no fractions, one term by itself. Let's try to do this by rewriting stuff. Well, I have, both of these terms have a cotangent of x in common. So one of the strategies that we talked about was we could try to factor using GCF, diamond, difference of two squares. If I have the same term in two places, I know that I can take out the GCF, which would be that term that I see. So if I see cotangent in both of these terms, I can take cotangent out, and I can rewrite this as cotangent of x times cosecant squared of x minus 1. And then off to the side, I'm going to talk about the identities that I'm going to be using, because I might have to rewrite them from the original way that I saw them in how they were given to me, or how we just talked about them. I know that if I see 1 and cosecant together, this brings me back to, so I see cosecant squared of theta and I see 1. Maybe I can use this Pythagorean identity to rewrite this. So I can maybe use cotangent squared of x plus 1 is equal to cosecant squared of x. Does this look, so I use the Pythagorean identities a lot to go from two terms to one. Right now on the left-hand side, I have cotangent of x plus 1 is equal to this one term here. But that's not what this looks like inside here. So I'm wondering if I could rewrite this identity so that one side, the side with two terms, looks like this. And then I could replace this with the one term on the other side of the equation. So I'm going to try to rewrite this. I want to get cosecant squared of x minus 1 on one side of this equation. So if I subtract 1 on both sides, I can get that. So I can say, okay, well, cotangent of x is equal to cosecant squared of x minus 1. And then I know that I can rewrite cosine squared of x minus 1 as just cotangent. So I can get rid of two terms and make it one term. So instead of writing cosine squared of x minus 1, I can write cotangent squared of x, and that multiplied by cotangent of x. I just changed this to be this. The goal is to get down to one term. So now if I can combine these things. They're like terms, or well, that's not really how I'd say that. So I would have cotangent cubed of x, and this would be my one term that I got everything down to. So I went from this, I simplified. Let's try another. So B, I have tangent of x times sine of x plus cosine of x. Off to the side, I want to write the identities that I'm going to be using, because I may have to rewrite them like I just did for the Pythagorean identity I looked at. I'm not seeing that these terms are factorable. Let's look at the other things. So I can't really do this. I can't get a common denominator. They're not fractions. I can't multiply the denominator by a conjugate. I can't split up a fraction. There is no fractions. I could rewrite everything in terms of sine and cosine. Or I can substitute using trig identities. So I'm going to try to rewrite everything in terms of sine and cosine, but that will require rewriting using identities that I know. So I have sine and cosine here. I just would want to change tangent of x into sine and cosine. So I know that I can say, well, tangent of x in terms of sine and cosine is sine of x over cosine of x. So over here, I'm going to rewrite this as sine of x over cosine of x. And then I know that I'm multiplying by sine of x and adding cosine of x. I'm going to change sine of x into a fraction, so I'm going to put it over 1. And then what I'll see is that I have sine squared of x over cosine of x plus cosine of x. Now I have two fractions that I want to add together. And in order to do that, I'm going to need to have a common denominator. So I'm going to rewrite this as a fraction by putting it over 1. And then I'm going to change this so that it has a common denominator. And in order to do that, well, what's the common denominator, the least common denominator? It would be just cosine of x. This is 1. I can very easily change that into cosine of x, and then they'd have the same denominator. So to do that, I don't want to change the value of the fraction. I just want to change the denominator. So I multiply by a giant 1. This is a giant 1 cosine of x over cosine of x. And then I'm going to get, I have a sine squared of x over cosine of x plus cosine squared of x over cosine of x. And when I add these two together, I'm going to have sine squared of x plus cosine squared of x all over cosine of x. From here, I see something that, I recognize it very easily. I see something, these two terms here go together. I'm looking out for sine squared of x and cosine squared of x to be together because I can rewrite those as one term using that Pythagorean identity I have. So this Pythagorean identity here has cosine squared of x and sine squared of x together, and I can use that identity to simplify that numerator. So I could say, okay, I know that sine squared of x plus cosine squared of x is equal to 1. So instead of writing this, I can write 1. I can say this is actually 1 over cosine of x. I just changed sine squared of x plus cosine squared of x to be 1. And I'm going to rewrite this. Using another identity that I know. A third identity that I know is, I can say that 1 over cosine of x, because I don't like fractions, no fractions, is equal to secant of x, the reciprocal of cosine. So I can say that my final answer is one term, and it's just secant of x. And that's my answer. So I just rewrote 1 over cosine of x as just secant of x by itself. Okay, for C, I'm going to talk about the identities that I'm going to be using. First, I'm going to look at this expression and see what does it look like, what can I do with it. Well, I have cosine of x minus pi over 2 times cosecant of x. This looks kind of familiar to me. That looks kind of familiar to me, and I want to know, I'm going to look back at my trig identities to see what it looks like. Well, if I go up here, it looks like cosine of pi over 2 minus theta is equal to sine of theta. So that's what it looks like. I'm going to write this down over here. So I'm going to say, okay, I know that cosine of pi over 2 minus x is equal to sine of x. Does that look exactly like that, though? No, it does not. So what I would have to actually do first before taking care of this trig identity, so before I touch on this, I have to think about how I can change this. So how can I change this to look like that? And what I could do is I could say, okay, I could rewrite this as cosine of pi over 2 minus x, which is what I see here. If I think about what kind of function cosine is it odd or even? Just flipping these things to their opposites, so flipping this to its opposite and this to its opposite, would really be like putting in this, but the negative version. And if I do that, I know that stems from the fact that if I do cosine of negative x, it's going to give me the same thing as cosine of positive x because cosine is an even function. So if I know that cosine is an even function, I could literally just rewrite what I had originally as I can just change what's inside to its opposite, and it means the same thing. So that's what I am going to do. And then now that I have it in the form for the second identity, I can use the second identity to rewrite this further. So this is still being multiplied by cosecant of x. From here, I'm going to use the fact that cosine of pi over 2 minus x is equal to sine of x to rewrite this complicated looking thing as just sine of x. So I have sine of x times cosecant of x. I just rewrote this thing here, because it's this thing here, as sine of x. So I made it simpler. And now I have this. And from here, the only thing I can do is write everything in terms of sine and cosine, in this case just sine. I can say, well, I have sine of x times, and then I can change cosecant of x. If I wanted it to be in terms of sine, I could make it 1 over sine of x. And so I would write this as 1 over sine of x. I have sine of x over 1 times 1 over sine of x. This and this is going to cancel. I use a different color. And I'm going to end up with, this is just going to be equal to 1. So my final answer is just 1. Okay, then I'm going to do d. So I have cotangent of theta times sine of theta times secant of theta. And the only thing of the strategies we talked about that I think I can use is changing everything to sine and cosine. So off to the side, I'm going to write the identities that I'm going to use. And I'm going to try to change everything to sine and cosine. First off, I can change cotangent of theta to be, in terms of sine and cosine, I can change it to be cosine of theta over sine of theta. So I'm going to write cotangent of theta as cosine of theta over sine of theta. And then I have that times sine over theta, sine of theta over 1. If I write it as a fraction, I'm just rewriting this as a fraction. And then to rewrite secant of theta in terms of sine or cosine, well, I can say, okay, secant of theta, I know I can write in terms of cosine, and I can say it's 1 over cosine of theta. So I can rewrite secant of theta as 1 over cosine of theta. So to recap, what I've done so far is I have rewrote cotangent of theta as cosine of theta over sine of theta. And I've rewritten secant of theta as 1 over cosine of theta. And now I'm going to try to see if there's anything that cancels. I know diagonally speaking, I can cancel the cosine and the cosine. I can cancel the sine and the sine. And once again, I am left with just 1 in the numerator and 1 in the denominator, so just 1 is my answer. And then, why is there 2 C's? This should be E. That's weird. I have secant of t over tangent of t minus tangent of t over 1 plus secant of t. What I want to do is, these are 2 fractions that I want to combine. So one of those strategies that we talked about to write this as one term is to come up with a common denominator. So off to the side, I'm going to think of, okay, what's the LCD? Does this fit into this? Could I multiply tangent of t by something to get 1 plus secant of t? No. So this LCD is actually going to be these 2 things multiplied together. So tangent of t times 1 plus secant of t. And so I'm going to have to multiply the first fraction. I guess I have to write it like, I don't know, I'll write it like this. The first fraction, I'm going to rewrite, or I'm going to multiply by 1 plus secant of t in the denominator. And if I do that in the denominator, I've got to do that in the numerator, because I want to make, I want to keep that fraction the same value. I'm multiplying by a giant 1. I'm going to subtract, or I'm subtracting tangent of t over 1 plus secant of t, and I want to change that denominator to be this. So I need to multiply that denominator by tangent of t. And if I do that in the denominator, I'm going to have to do that in the numerator to keep it, to make it a giant 1 that I'm multiplying by, so that the value of that fraction doesn't change. And then I'm going to multiply through. So I have secant of t times 1 plus secant of t times secant of t. So that's going to give me secant of t plus secant of square root of t all over, and then I just have, I'm going to leave it factored for right now, tangent of t times 1 plus secant of t. And then my second fraction in the numerator, I'm going to have tangent square root of t, because I'm multiplying this times this. And then in the denominator, same thing, tangent of t times 1 plus secant of t. I'm going to leave it factored. From here, I'm going to combine my numerators. So I'm going to say, oh, well, I have secant of t plus secant squared of t minus tangent of tangent squared of t, all over tangent of t times 1 plus secant of t. Okay, from there, I'm going to try to find something that I could do. I am noticing that I have, and something I'm going to try to look out for is if I have secant of squared and tangent of squared together, because that's one of the Pythagorean identities that we talked about. So tangent squared and secant squared of theta together. If I have those, I could probably rewrite them as one term using a Pythagorean identity. So that identity that I would be using is going to be the one that says I have tangent squared of, and I'm going to change the variable to t because that's what I have here, plus 1 is equal to secant squared of t. And this is not exactly what it looks like here, but maybe I can rewrite this to get it to look like that. If I wanted secant squared of t minus tangent squared of t on one side, so I could rewrite the two terms as one term, I would subtract tangent squared of t on both sides. And I would get, okay, secant squared of t minus tangent squared of t is equal to 1. So I can say, okay, well, these two terms I can write as just 1. And that's what I'm going to do. I'm going to rewrite this as secant of t plus just 1 all over, I have tangent of t times 1 plus secant of t. And so all I did there was I just changed this to be just 1, or just 1. And then from there, what I noticed is that I have secant squared of t plus 1 in the top and the bottom, and I can cancel those out. And I'll be left with 1 over tangent of t. I don't like fractions, so I'm going to use the fact that 1 over tangent of t is equal to cotangent of t. And so my answer is cotangent of t. And that's it. I just changed 1 over tangent of t to be just cotangent of t. One term.